You ever see a big scientific headline and wonder, how did they even start? How does a simple question turn into, a huge groundbreaking study? Well, it's not magic, that's for sure. It turns out every single discovery, every news report, every breakthrough, it has a blueprint, just like an architectural plan for a building. And today, we're going to learn exactly how to read it. So it always starts with just curiosity, right? You might see something happening around you and ask a question like this one. Do students struggle with mental health? And look, that's a great question. It's a fantastic starting point. But for the world of actual research, it's kind of like trying to build a skyscraper based on a sketch you drew on a napkin. It's a little too vague. And that's because science absolutely demands precision. To get a real, meaningful, reliable answer, we have to go way beyond that broad curiosity and get super specific. We need a question that we can actually measure and test out in the real world.
Okay, now this is a question. See the difference? It is so much sharper, way more focused. We've defined our population, we're talking about college students. We've defined the time frame, specifically their first year, and we've defined exactly what we're looking for, symptoms of depression. This is not a napkin sketch anymore, this is our blueprint. It gives us a really clear target to aim for.
So you gotta remember, that super specific, carefully crafted research question, it isn't just a formality. It becomes the master plan. It's the North Star that guides every single decision a researcher is going to make from here on out. And just like an architect can design a skyscraper or a little house or a massive bridge, researchers have different kinds of blueprints for different kinds of questions. And these questions usually come in 3 main flavors. And this table here breaks it down perfectly. First up, you've got your descriptive questions. These basically ask, what's going on? Think of it like taking a snapshot in time. What percentage of students are depressed? Simple. Then we have correlational questions. These ask what things are related. It's all about finding patterns, like, is more time on social media linked to lower self-esteem? Now, notice it's not saying one causes the other, just that they seem to move together. And finally, you've got the big one, causal questions. These ask what causes what? Does exercise actually reduce anxiety? This is the toughest one to prove, but it's often the one we want to know the most. All right, so you've got your blueprint, you've picked your research question. What's next? Well, now you have to pour the foundation. And in the world of research, we call that foundation a hypothesis. Now, a hypothesis isn't just some wild guess you pull out of thin air. It's a really educated, testable prediction that's based on what we already know from other theories or studies. And that word, testable, it is everything. If you can't design an experiment to prove it right or wrong, then I'm sorry, but it's not a scientific hypothesis. So, how in the world do you make something testable? You do it with something called an operational definition. This is such a critical concept. It just means you define your big abstract ideas in really concrete, measurable terms. So you can't just measure intelligence. It's too vague, but you can measure scores on a standardized IQ test. And that kind of precision is what allows other scientists to come along, replicate your study, and see if they get the same results. It's crucial. When an architect designs a building, they have to plan for everything. Wind, rain, earthquakes, you name it. Well, a researcher does the same thing by creating 2 competing hypotheses. It's a pretty clever way to avoid being biased and to really rigorously test their own ideas. So this brings us to this little battle of ideas that researchers set up. On one side, you've got the null hypothesis. You can just call it H0. Think of it as the ultimate skeptic in the room. It's the default position that says, nope, nothing to see here. Meditation has 0 impact on anxiety. Then on the other side, you have the alternative hypothesis, or H1. And this is what the researcher actually thinks is going to happen, that meditation will reduce anxiety. The whole goal of the study is to gather enough evidence to be able to knock down that skeptical null hypothesis and say, see, there really is an effect here. Okay, so we've got our blueprint and our foundation is poured. Now we need the actual building materials for our experiment, and those materials are called variables. First up, we have the independent variable, or the IV. You can think of this as the cause in any cause and effect relationship. It's the one thing that the researcher is intentionally changing or, manipulating to see what happens. So in our running example, it's whether a person meditates or doesn't. And if the independent variable is the cause, well, then the dependent variable, the DV, is the effect. It's the thing the researcher measures to see if their change actually did anything. So did meditating change the participants' anxiety levels? That's what we're measuring. But of course, to run a fair test, you have to control the environment, right? Control variables are all the other things you purposefully keep exactly the same for every single person in the study. Things like, I don't know, the age of the participants or the quiet room where they're being tested. This just makes sure that the only major difference between your groups is that one thing you changed, the independent variable. But here's where things get dangerous: confounding variables. These are the sneaky, hidden factors that you didn't control for, and they can creep in and completely mess up your results. Like, what if the meditation group just happened to get more sleep the night before the test? That's a confound. It could be the sleep, not the meditation, that lowered their anxiety. And this kind of thing can threaten the validity of the entire study. So we have the blueprint, we have the foundation, and we have the building blocks. Let's actually see how all these pieces come together in one of the most famous and controversial experiments in the history of psychology. This is Stanley Milgram. Back in the 1960s, he was fascinated by obedience to authority. His huge question was, how far would an ordinary person go in obeying an instruction if it meant harming someone else? I mean, what a powerful causal question, right? And here's the architecture of his study, just laid bare for us to see. The question was all about obedience. The hypothesis was that an authority figure's instructions could literally make someone act against their own conscience. The independent variable, the thing he actually manipulated, was the authority figure's commands to continue. And the dependent variable, the effect he measured, was the level of fake electric shock the participant was willing to give someone. It was a perfectly constructed experiment, even if it's still debated ethically today. So, what this all shows us is that having a clear structure, a specific question, a testable hypothesis, and really well-defined variables, that's the engine that lets science go from just a vague curiosity to a powerful and, yeah, sometimes shocking conclusion about how we all work. So now you have the blueprint. You know the language of research architecture. So the next time you see a headline about some new scientific finding, I want you to ask yourself, can I see the structure here? Can I spot the variables? Can I see how it was built?